For our next piece of section 4.4, we've learned about the first fundamental theorem of calculus. We now need to get into the second fundamental theorem of calculus, but before we do that, we need to try to make sense out of these functions that are defined by integrals. The notes for this video are going to go on a sheet that you have titled section 4.4 functions defined by integrals notes. Please find that sheet. I'll make the video pause. Let's take a look at this first problem. Consider the function f of x, which equals the integral from 0 to x of g of t dt, where g of t consists of line segments in a semicircle shown below. Okay, so this thing over here is g of t, okay? Actually, I'm going to cross that out. It should really be a t there, whatever. Made up of line segments in a semicircle over here. We are asked to, let's see, find f of 6 and f of negative 7. Well, the deal is there are two different functions. There's the f function and there's the g function. G is the graph that I'm looking at, but f is defined as the integral from 0 to x of that thing. So really, f of 6 means I'm going to plug in 6, not really like into the function itself, but I'm going to plug it in as that upper limit of integration. F of 6 is the integral from 0 to 6 of g of t dt, which means f of 6 is going to be the signed area under that g function starting from 0 going to 6. Well, I think you can figure that out. What are you going to get for that? Let's see, I've got a triangle above the x-axis, 1/2 times 4 times 2, and a semicircle below the x-axis, minus 1/2 times pi times 1 squared. I am thinking 4 minus pi over 2. F of 6 is 4 minus pi over 2. Next, f of negative 7. By my formula, that should be the integral from 0 to negative 7 of g of t dt. Oh, you know what? I don't really like what this looks like. I'd rather, when I have a graph, go from my lowest value to my highest value. So I'm just going to switch my integral around, change the limits of integration, which I'm allowed to do as long as I also do what? By our properties of integrals, as long as I also change the sign of this, I'm okay. So I'm going to get negative. You go do that. Find your signed area from negative 7 up to 0. I see a rectangle, then a triangle. Deal with it. Let's see, this rectangle's below the x-axis. Negative. Base is 3, height is 2, so negative 3 times 2. Then there's a triangle, minus 1/2 times, base is 4, height is 2, 1/2 times 4 times 2. This is negative. Negative 6 minus 4. This is negative 10. We're going to get positive 10 out of that. These functions defined by integrals have our variable in one of the limits of integration. So really all I'm doing is plugging in my number for the limit of integration and then using signed area ideas to evaluate. Turn the page over. New one. Capital F of x is defined as the integral from 0 to x of little f of t dt, where f of t is shown on the graph below. Okay, so this is f of t. We are asked to find all sorts of values of f of x. Let's see here. I'm asked to find f of 0. Well, f of 0, capital F of 0, is the integral from 0 to 0 of little f of t dt. So the area starting at 0, ending at 0 under that curve. We've got a property of integrals that says what this is. What is capital F of 0? Capital F of 0, I think that's just 0. Fill that into my table. Capital F of 1 is the integral from 0 to 1 of f of t dt. What's that? Well, I'm going to be dealing with that triangle over there. 1/2 times 1 times 1. I think that's going to be a half. Capital F of 1 is a half. Capital F of 2 is the integral from 0 to 2 of f of t dt. Another name for these functions defined by integrals are accumulator functions, because I keep accumulating area. Capital F of 1 is this thing. Capital F of 2 also includes this thing over here. I'm just accumulating this area. Well, what is capital F of 2? 1/2 times 2 times 2, I'm getting 2. Capital F of 3, do the integral from 0 to 3 of f of t dt. See what you can get. Okay, so I've got to add in this piece over here. Ugh, that's a pain. How about I do, okay, what I had before, 2, plus the triangle up top, plus the square below it. So maybe 2 plus 1/2 times 1 times 1, plus 1 times 1. I think that's 2 plus 1/2 plus 1. I think that's 3 plus 1/2. I'm thinking 7/2. F of 4. F of 4 is the integral from 0 to 4 of f of t dt. Triangle, base of 4, height of 2, 1/2 times 4 times 2. We're getting 4. Now, my accumulator function, as I continue, will my answers continue increasing, or will they start decreasing, and why? As I continue on, I'm now going to be accumulating negative area, so that's going to start subtracting from what I had. F of 5 is going to be the integral from 0 to 5 of little f of t dt. Why don't I take what I had for f of 4, and I'm now going to subtract this triangle because it's below the x-axis. 4 minus 1/2 times 1 times 2. 4 minus 1, I think we're going to get 3. You go find f of 6. What I had minus that rectangle, minus 1 times 2, 3 minus 2, we're going to get 1. And finally, find f of 7. Take what you had, subtract that triangle. I'm getting 0 for that final answer. I now ask you to graph f of x. So I'm going to plot those points that I just calculated. 0, 0, 1 comma 1/2. By the way, these are not negatives. That's just the grid line getting extended. Don't get confused by that. 1 comma 1/2, 2 comma 2, 3 comma 7/2, that's 3.5, 4 comma 4, 5 comma 3, 6 comma 1, 7 comma 0. That connect the dots? Oops, kind of like this. We're asked what the relationship is between these. Well, notice that as my area keeps increasing, this thing over here is going up. As soon as I start adding in some negative areas, this thing is going down. Notice that this thing is increasing while this graph is above the x-axis. When this graph has values below the x-axis, this graph starts decreasing. This should sound familiar to you. We looked at some of the stuff when we did our curve sketching stuff. I think that little f of t is the derivative of capital F of x. F of t is the derivative of capital F of x. Or another way we can think about this, super clear. Another way we can think about this is capital F of x is the antiderivative of little f of t, really little f of x. I can change my value over there to that. More with this as we move forward, but these are some of the ideas we're going to see in our second fundamental theorem of calculus.